Eternal inflation. Eternal inflation proposes that the universe began with a phase of extremely rapid expansion, driven by a high-energy field called the inflaton. In some places, this expansion ended, converting energy into particles and radiation, producing conditions like the hot Big Bang. But in other regions, quantum fluctuations kept inflation going. As a result, space as a whole keeps expanding eternally, while isolated patches reheat into self-contained bubble universes. Our observable universe can be understood as the inside of one such bubble. Inside each bubble, cosmic evolution follows familiar stages. Matter forms, galaxies condense, and cosmic background radiation cools. These bubbles are usually born with slight negative curvature, though additional inflation inside them flattens their geometry. If neighboring bubbles form close together, they can collide, leaving possible imprints in the cosmic microwave background. Scientists have searched for these signatures but haven't found clear evidence, placing limits on how often such collisions could have occurred. Because eternal inflation produces infinitely many bubbles and observers, it creates the measure problem, a difficulty in defining probabilities when every outcome happens infinitely often. It also may not be past eternal, since theorems suggest an earlier boundary or mechanism is required. Observationally, eternal inflation explains why our universe looks flat and uniform, but the multiverse itself remains difficult to test directly. Indirect searches focus on fine features in the microwave background, constraints on cosmic curvature, and consistency with high-energy physics. The Big Bounce. The Big Bounce replaces the idea of a singular beginning with an endless cycle of contraction and expansion. Instead of space and time starting at a singularity, the universe undergoes a prior phase where it contracts, reaching a minimum size before bouncing back into expansion. This avoids the infinite density and temperature problems of the standard Big Bang. In some models, quantum gravity effects prevent a total collapse, forcing a rebound when density reaches a critical point. A bouncing cosmos could mean our universe is just the latest cycle in a series of expansions and contractions. Each cycle might reset conditions, but traces of earlier universes, such as specific patterns in cosmic microwave background radiation, might survive. Researchers look for non-random features in temperature fluctuations or anomalies in primordial gravitational waves to test whether a bounce preceded our Big Bang. The Ekpyrotic Universe. The Ekpyrotic model proposes that the universe began when two three-dimensional branes collided within a higher dimensional space. This collision injected enormous energy, igniting conditions similar to the hot Big Bang. Unlike inflation, which stretches space, the ekpyrotic scenario smooths and flattens the universe by compressing it before the brane impact. This theory comes from string theory and extra-dimensional physics. The brane collision explains why the universe is nearly uniform on large scales, while still allowing small fluctuations that seeded galaxies. However, it requires exotic assumptions about extra dimensions that we cannot yet test directly. Scientists continue searching for distinct signatures, like unusual gravitational wave spectra that would separate it from standard inflation. Quantum creation from nothing. In some quantum cosmology models, the universe could emerge spontaneously from nothing. Here, nothing does not mean absolute emptiness, but the absence of space, time, and matter as we know them. Quantum tunneling allows a universe to appear as a self-contained bubble, starting small and then inflating. This idea relies on the principle that in quantum mechanics, vacuum fluctuations can briefly create particles from empty space. Applied on a larger scale, a quantum fluctuation could produce an entire universe. Energy conservation isn't violated because the positive energy of matter and radiation can be balanced by the negative energy of gravity. In this picture, time itself may have begun with the universe, meaning there was no before. String gas cosmology. String gas cosmology imagines that the early universe was filled with a hot gas of fundamental strings rather than point-like particles. In this model, extra-spatial dimensions exist, but most remain curled up and invisible, while three dimensions grew large to form our universe. The gas of strings determines which dimensions expand by their winding and vibration states. This scenario can explain why our universe has three large spatial dimensions instead of more. It also naturally avoids the singularity problem because the string gas provides a maximum temperature, preventing infinite heating at the origin. While intriguing, it depends heavily on string theory, still an unconfirmed framework, and lacks clear observational evidence to date. Loop quantum cosmology. Loop quantum cosmology applies loop quantum gravity, a theory that quantizes space and time, to the early universe. In this view, space is not continuous but made of discrete chunks. When the universe contracts to extremely small scales, quantum geometry generates a repulsive force that prevents a singularity. Instead of a Big Bang, the universe experiences a quantum bounce. This predicts that the universe had a prior contracting phase before rebounding into expansion. Unlike classical general relativity, which leads to infinities at the singularity, loop quantum cosmology gives a finite, calculable structure at the bounce. Observationally, researchers look for imprints of this prior phase in the cosmic microwave background, such as specific deviations from standard inflationary predictions. The holographic origin. The holographic principle suggests that our universe could be a projection of information encoded on a lower dimensional surface. In this model, the beginning of the universe isn't a point-like explosion, but the unfolding of information stored on a two-dimensional boundary. The three-dimensional world we observe would then be an emergent holographic projection. This approach arises from black hole physics. Black holes hold information about everything that falls into them, not in their volume but on their event horizon. Extending this logic to the cosmos, the entire observable universe could be described by data stored on a distant surface. This eliminates the need for a singularity at the Big Bang, since the origin lies in encoded information, not infinite density. Testing the holographic origin is challenging, but cosmologists look for mismatches between predictions of standard inflation and actual cosmic microwave background data. If the universe is holographic, subtle correlations in primordial fluctuations, beyond what inflation predicts, might be detectable. So far, evidence is inconclusive, but this framework remains one of the strangest attempts to redefine the universe's beginning. Conformal cyclic cosmology. Proposed by Roger Penrose, conformal cyclic cosmology states that the universe undergoes an infinite sequence of eons. Each eon begins with a Big Bang and ends in extreme expansion, where all matter decays into massless radiation. At this stage, with no mass to define time or scale, the universe can be mathematically rescaled into a new Big Bang for the next eon. The idea hinges on the conformal symmetry of spacetime, which allows physics to ignore absolute scales. When everything becomes radiation, the infinite future of one universe looks mathematically identical to the very beginning of another. In this way, there is no single beginning. Instead, universes pass the baton endlessly. While controversial and not widely accepted, this model offers a radical alternative to inflation and gives the Big Bang a cyclical, rather than singular role. Vacuum fluctuation models. Quantum field theory describes even empty space as filled with fluctuating fields. These fluctuations can momentarily create particles and energy out of nothing, though they usually vanish quickly. Some cosmologists propose that our universe could be the result of one such fluctuation that did not collapse, but instead expanded into a full universe. This model treats the Big Bang as a rare but possible statistical event in a sea of quantum foam. Because quantum mechanics permits small-scale violations of energy conservation for brief times, a universe could arise provided the total balance of positive and negative energy sums to zero. Gravity's negative energy allows such balancing, making the creation of a universe energetically plausible. The challenge is that vacuum fluctuation models blur the line between something and nothing. The quantum vacuum is not true emptiness, but a background governed by physical laws. Thus, the beginning of the universe in this model might still depend on pre-existing rules, rather than being absolute creation. Emergent universe models. Emergent universe models suggest the cosmos never began from a singularity, but instead existed forever in a quasi-static state before transitioning into expansion. In this scenario, the universe starts off stable, unchanging, and eternal, only later entering a phase of growth similar to the Big Bang. This bypasses the problem of time starting at zero. Instead of asking what happened before the Big Bang, these models argue that the universe has always existed in some form. The eventual trigger into expansion could come from quantum fluctuations, instability in a scalar field, or other high-energy physics effects that break equilibrium. Observationally, emergent models predict subtle differences in the cosmic microwave background compared to standard inflation. Because they avoid a true singularity, they also provide a framework where time stretches infinitely into the past. This makes them appealing to those seeking a universe without an absolute beginning. Pre-Big Bang string theory. The pre-Big Bang scenario, based on string theory, argues that our universe emerged from a collapsing state rather than a singular birth. According to this model, the cosmos once existed in a cold, empty, low-curvature phase. Then, under the laws of string theory, it underwent a period of acceleration that reversed contraction into expansion. This approach reimagines the Big Bang as a phase transition rather than a true beginning. Instead of space-time tearing from nothing, it evolves from a prior string-dominated state into the hot, dense plasma we associate with the early universe. The transition could leave observable traces in the form of gravitational waves with unique signatures. However, the theory relies on unverified aspects of string theory, such as extra dimensions and dualities between expanding and contracting phases. If detectable, these stringy signatures would offer insight into the very high-energy frontier, far beyond current particle accelerator experiments. Simulated universe hypothesis. One of the strangest ideas is that our universe began not physically, but as a programmed simulation created by an advanced civilization. In this hypothesis, the Big Bang could be equivalent to the moment the simulation was started, with the laws of physics defined by its code. This model is less about cosmological physics and more about computational philosophy. If it is possible to simulate universes in the far future, then, by probability, we may already live inside one. Our cosmic beginning would then be artificial, generated by computation rather than physical processes. Detecting this scenario would mean finding glitches or anomalies in physical laws that suggest underlying computational limits. Some physicists argue that patterns in cosmic rays or discretization in space-time might reveal such evidence. While speculative, the simulated universe hypothesis forces us to question whether the cosmos has a real beginning at all. Thank you for watching this video. If you have enjoyed watching, please leave a like and subscribe, and let us know in the comments if you would like to see more videos like this one.